I do not take that personally at all. It's my fault. Or it's just a reminder when I get busy. All right, so we're going to start today by actually writing insertion sort, because it's one thing to see the pseudocode and to see it drawn, see the logic drawn, but now we want to tie the logic of how is this sort happening to how do we write the code that ensures that it happens. So who had a chance to finish this off between yesterday's class and today's class? Further proof that if you don't assign it, it doesn't get done. I'm not using that as judgment by any means, but it's just something that professors need to be aware of. If you don't assign something, you can't expect that people do it. All right, so we're eventually going to have kind of a main driver. I'm not going to make it a separate class. I'll just have some things that we write eventually, but we're just going to make an insertion sort method that's going to take an array, a basic array. This does not need to be an array list. And it's the question I guess I can ask you, what should insertion sort return? Some kind of sorted list? Do we need to return it? Oh no. It's being passed by reference, right? If it's an object like an array or an array list or any other kind of object, it's passed by reference, which means that we are duplicating that reference variable. We're doing a shallow copy of it so that we're working with the same object. We may just be calling it a different name in the scope of our main and in the scope of our insertion sort. So we're going to what do we want to call our array? I like a list. List, array, something that tells us that when we see it, we know exactly what we are modifying. And we don't want to make it a or anything that is short or is ambiguous as to what it might be referring to. This is our original list. Great. All right. How do we start? I kind of want to pull up, is this going to work? Can I pull up I guess what I could do, let's see if I can just grab this, throw it in, or even better, I could snip it. So now we have access to this that hopefully we can just pull up if I resize this to be as small as we can get it. When we need to refer to this, we'll just bring it up. This is why I like having multiple monitors. I don't get multiple monitors here, which is unfortunate. Sorry, I'm mostly better, but still get the occasional. So, all right. Insertion sort, the first thing we want to say is mark the first element as sorted. What does that entail in code? Just need like a sorted index, starting at 0. Okay. Do we want to start it at 0? If we say we want to mark the first element as sorted, is there any work that needs to be done to the 0th element? The 0th element is already going to be sorted. So this tells us that our outermost loop that's going to go through and for each element of the array, kind of move it back into its place in the left-hand sorted array. We're going to start with index 1 rather than index 0. So we don't actually have a to-do item for that first thing, but we can say that, let's say, for what do we want to call this counting variable? What does it represent? Count is a really generic counting. That's true if there's maybe one thing that we're going to be counting, But we need to, one, keep track of which is the current element that we are on, and then where are we moving it back to? So we're gonna have multiple different counting variables. So we would like something that tells us something a bit more specifically what this is. So I could call this something like step. And then in step 1, we're going to be moving that back into place. Step 2, we're going to be moving index 2 back into place. So we said that we wanted to start this off at 1. What's the termination condition for step? So list dot length. Is it list dot length minus 1, list dot length minus 2, list dot length plus 1? Minus 1. So one thing to note is this is a strictly less than. So let's say the list is of size 10. We want to go from 1 up to 9. We want to make sure that we do get that last element. So 9 is the length minus 1, but this strictly less than is going to mean that we want 1 more than that. So I don't actually want straight list dot length.
Could you change the theme to dark? It's just hard to see.
Yeah, I guess I can blow it up
Just
too.
white it out. Oh, that helps.
But it'd be easier to see if I did dark mode remotely as well. Probably not. I don't know. Does anyone remotely have an opinion on that?
I think it's the light.
We turned our lights off?
Yeah, it kind of blinds the, I can totally see that from. If we do that, is that better? It's,
Oh, yeah, clearly, but like, yeah, it's like a fucking hit.
especially if you write on it.
But like. Turn the lights off, my fault.
Each time around, we're gonna be bumping up the step. All right, so what do we need to do for each one of these? So now we've come up with a logic that isolates now each element that we now need to move back into place in the sorted array. So yeah, now we need some way to say something like we need to move it back. We need to start comparing it to values that come before it in the array. And we need to start deciding whether we need to write that, and we need to store off the current element somewhere. So let's start by storing the current element. So we could say something like int list of, what's the index for list? Yep. That seems right. Everyone agree? All right, so now we've stored it off. Now we're okay to overwrite it. So what is the logic? What should we say for how to decide whether we need to overwrite it or not? If we use an if statement right here, how many times are we going to possibly do this for each one? A single time? We may need to do it a bunch of times, depending on how far back we're going to be moving in the sorted array. So I think we need some kind of inner loop here. What would this inner loop look like? Yeah?
I made a previous integer and I made a while previous is less than or equal to 0. Would that work? Or-
Something like that, yeah. So I like that. So we'll use some kind of while loop here. So we can say something like while the previous element. So how could we access the previous element? Maybe we do want to store off. It seems like we might be using this previous element multiple times. So rather than repeating the same expression over and over, maybe we want to store it in some kind of. Something like that. This would be the index of the previous element, so maybe we should call this prev-index. Something that is again very descriptive. If we said prev, that would usually be something like the value of the previous, which is not what we want. We want the index of the previous. So while I guess we have a couple of, before I start typing and just doing things, we have a couple of things we need to check here. What are those two logical conditions that could stop the terminate or could terminate this loop? Yeah, if we reach the beginning of the array, so we go all the way to the beginning, we don't want to try to access a negative index. So the last time that prev-index could be valid is what?
4.
Could it be 0? It could be. The 0th index is going to be the first element, and we would want to make sure that we can compare that and override it. So we could say something like greater than or equal to 0. So that's the first thing. We need both of these things to be true. We need the index to be valid. And what means that we want to do the override? Yeah,
The current is less than the item at the previous index.
yeah. Something like that.
Why didn't you do the, why didn't? Oh, actually, never mind. I'm kind of just confused on the prev index and why didn't you do like a list? Why don't you make it a part of the array list for the array?
Because list of prev-index is going to tell us the value at that. So we have an easy way of referring to it. Prev-index just now says that we don't need an expression in here.
I was more talking about the actual initialization of prev index.
So. Say that again.
Why didn't you list? Why don't you make it?
List of step -1. Because that would be whatever is stored there -1. So let's say the value. Right, a really small array. So something like we have an array of 3 elements. We have 8, 9, and 4. So we know that this is sorted, right? So now, if we're trying to figure out where this position should be, let's actually do this so that we can want to swap them. So I'll just make this 8, 4, 9. So this would now be current. So current is going to be list of step. So current is 4. Step is 1, it's the index. So now if we say prev-index is step -1, this is prev-index. If we were to say something like current -1, it would be setting it to 3. Does 3 have any use or validity in any of the computations that we need here? We want to say, we want to compare whatever's at this position in the array, to whatever's at this position in the array. So we want to compare the value of current to whatever is at the value at prev-index. So list of prev-index says compare 4 and 8. Does that make sense to people?
Yeah.
So if you couldn't come up with this off the top of your head, and no pressure at all to come up with something like this off the top of your head, that comes with practice and just being able to visualize the problem, then what we want to do is draw out something like this. Choose a very small example. There's no reason for this to be any larger than 3. Even 3, we're not using this 9 or this 2 at all, so we could just do it with an array of size 2, make it as small as feasibly possible to figure that out. And then start thinking about, all right, in this example, what are the variables? Where are they? And that can help you to identify what is it that I'm actually trying to do visually and logically with this example. As you do this, mapping this to that logic will hopefully be a little bit easier than just trying to come up with it and visualize it in your head. Everyone good with what's on the board? Can I erase it? All right, inside of this loop, now we have pre-index. We know what that is. It's the index of the previous. We named it well, since I can't think of a better way to describe it. We have current, which is the value of the current index, and list of pre-index is the value at the list at pre-index. So what is the comparison that we want to make between these to determine if we want to override what is at list of current with what is at list of pre-index? Or list of step. Already done that logic, haven't we? It's embedded in current is less than list of pre-index. If current is less than list of pre-index, then we want to override it. So what does the override look like?
Well, we're gonna store out the temporary value.
I think we already did. I guess, yeah, but this is the value, so we don't really want to use current here, do we?
I defined an integer temp and I set it to the list dash or list current. Was the first step.
Yeah,
Step.
well. What are we thinking? Because we're never really modifying this current, right? We're moving it back into place. So I think we still do want current here, but what's going to be changing is this value of pre-index. We need to move back pre-index and then compare it to whatever comes after that. Move it back, compare it, move it back, compare it, move it back, compare it. So I think this is right. And I do not think we need a temp. So the override is going to look like list of. We need to override something to do with pre-index and something else to do with pre-index. So the current place in the list is going to be pre-index plus 1. Something like this. Does this look right to people? So I would want to use step here, but that's going to change. If we do this and then we bump down pre-index. Sorry. So if we do this, we'll loop back around. Pre-index is going to be getting closer and closer to 0. And we're going to be comparing current, this value of where we want it to be in the list. It's going to be bumping down and down and down. So we're going to be comparing it to elements that are sooner and sooner and sooner in the list until this value is greater than what is currently greater than or equal to the value that is currently at that position in the list. Do people buy that this works? Maybe we should draw it out and see if we go through this logic with an example that it works the way that we expect that it should. So let's use that same example from before. We don't really need something that's particularly long to see if this is going to work. So let's choose 8, 4, and I don't know, 6. And that way we're going to have some work to do each time. So we're going to set step to 1. So step is going to point here. Current is the value for pre-index is step -1. So I guess I would rather point step here. That. All right. So while pre-index is greater than or equal to 0, which is true, and current 4 is less than list of pre-index, which is 8, is 4 less than 8. So we have true and true. So we're going to come into the while loop. We're going to say list of pre-index plus 1. So list of this gets list of pre-index. That's going to overwrite this. And note that we did set a current out there as list of steps. So maybe I should better write current out here, since we're storing that off and not referring to it anymore. Current is 4, and we're about to overwrite it, and this arrow won't make sense anymore. So we overwrite the 4 with an 8. We will bump down pre-index. So now pre is going to point here. Looping around, is pre-index greater than or equal to 0? No. Loop over. Is this what we expect? It is what we expect because there's one more thing that we want to do when this loop terminates, which is to insert this at the position of pre plus 1. Wherever this happens to terminate. If it terminates because of this, which we'll see the next time we do this, we just want to insert it into the position that we want. So now pre plus 1 right here gets current. So we can write the 4 in a way that's actually legible right there. Great. So now we're going to loop back around the outer loop, bumping up step. So now step is going to point at the 2. Step points here, current is list of step. So now instead of current being 4, I should write this a little bit larger so we can see it. Current is now 6. We'll store that off. Now pre is going to point out here. And we call it pre-index and just shorten it so that we can make sure we see it. Great. So pre-index is step -1, so that's currently 1. Is pre-index greater than or equal to 0?
Yes.
Yes. Is current less than list of pre-index?
Yeah.
Yes. 6 is less than 8. We'll come into the loop. We want to say list of pre-index plus 1 is list of pre-index. This will override the 6 with the 8. We'll bump down pre-index. So now this points here. Looping around, is previous index greater than or equal to 0? Yes. Is current less than list of previous index? Is 6 less than 4? No. Loop over. So now what we want to do is we want to write the 6 at list of previous index plus 1, just like we did before. So we'll take the 6 and we'll override it right here. So there's only one thing that's missing in our code right now, which is that line that does that overriding after this inner loop terminates and before the outer loop terminates. Questions? Does that make sense? And again, if I noticed that people were very quiet and not sure of this logic as we were going about it, but I think that if you draw it out like this with a very small example, that will help you to figure out, okay, what is the variable that I need to use? What is the assignment that I need to make in any of these places? We buy it? We buy that this works?
Yeah.
Having drawn it out and looked at it, I think it does. Just because we think it does, doesn't mean it actually does. That's what testing is for. But between this loop and this loop, we just need to say that list of prev index plus 1 gets current. We want to test it. Probably should verify that this actually works. And like we mentioned, we don't actually need to return anything because this list is passed by reference. So let's make just to be able to show that we can have these named different things or even the same thing, it doesn't really matter. I'll call this something else. What are the values we want to store in this array?
4, 6, 8.
Let's see, let's do like 8, 4, 6 again, just to see if it works exactly for that. And then we could do something like search and sort the array. Yeah, the issue is that this isn't a class of any kind, so this should be static. So now we want to print out the value of the array. How do you print out a value of a regular array? Yeah. We need to import arrays. So we can just very quickly make sure this gets imported. Oh my gosh. Now that we have this, we should be able to import. And then we just print that. Screen. There. Here, why are we calling this a capital I? This is the issue I was having before, where I think when I set this up, it was linked to the wrong JRE. That's why I have 2 of these. I can fix this. The issue, this should work. I'll try to make sure this gets fixed ahead of testing other things, but we should also test this out with other values of the array and make sure that it works for arrays. What other things could we test, especially those of you who are in 212? What is a reasonable additional test that we could do? What is likely to fail? Maybe an array of a single element, an empty array. Does this work for an array of a single element? Should.
Yeah, just. For instance.
Yep. Does it work for an empty array? Yeah, that's what it should do, because the actual toString for an array of no elements should be nothing. So you should not get a program that crashes. That's basically what we are looking for. We want to verify that this works for an array of an arbitrary size from 0 up to anything. Does it work for a list that's already in order? Does it work for a list that's perfectly in reverse order? It should. All right, so this will be our first sort. And I will upload this code ahead of anything that we need to use it for. Like I mentioned, the next assignment after the assignment that I assigned yesterday is going to be applying this concept to the linked lists that we have written. Because because this works for an array, we should also be able to make it work for our linked list. And it's a surprisingly little amount of work to make that happen. So the next thing we're going to do is we're going to learn about the next sort. No, not quite. We have a little bit of cleanup work to do. Let's talk about the complexity of insertion sort, because this is an important thing to know. So let's take a look at the worst case performance. So looking at the code that we just wrote, when is it going to perform at its absolute worst? When is it the most amount of work? Yeah, if the list is in reverse order, then every single element is going to need to be moved all the way to the beginning. We're going to be doing comparisons all the way to the beginning for each element. What does that look like? How much work is that for index 1? Since we don't worry about index 0, that's already sorted. For index 1, how many comparisons are we making? And we have to move it back 1. For index 2, we have to move it back 2. For index 3, we have to move it back 3. For index 4, we have to move it back 4. Have we seen this expression before? For however long the list happens to be. Did I mention that this shows up everywhere in computer science? It's back, and it will be back again before this class is over. But what did we determine was the order? Does anyone remember the expression off the top of their head for what the sum of 1 up to n is? Yeah, n times n plus 1 over 2, which is in order what? It's quadratic. So the worst case performance is in, we'll call it big O of n squared, even though the absolute worst case, if we identify that, but we know that it might perform better than its worst case performance. We've just identified an upper bound. It can't take more work than this. So we're going to call this big O of n squared. This is not big theta of n squared because it might run faster than this. We don't know yet. But it will not run worse than this. We've identified the worst case. How about the best case performance? What would an array look like where we minimize the amount of work that insertion sort has to do? Already sorted? What does that look like with regards to the pseudocode? Or the actual code? How much work is being done? What order is that in? We still need to verify for each element that it's in the correct position, but how much work is it to move each element into its correct position? It's a constant amount of work that we need to do for each element. So there are n elements that we need to verify don't need to move. So that's going to be linear. Does that make sense to everyone as to why that is linear? Feel free to shake your head and say, I do not understand that. That would help me to know why we need to do that. So we have a list that's in order. Let's just say it's the numbers. So we know this is already in order. This is going to be a single comparison that says, is this less than that? No. 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 How many questions did I ask? 4 questions for 5 elements? How would that scale if there were more than 5 elements here? N minus 1, which would be linear order. We don't have to do too much more work. Whereas on the other hand, what we just looked at, 5, 4, 3, 2, 1, if it's in reverse order, is this less than this? Yes. Are we at the end? Yes. Now this would be in order now. We would have swapped this to be 4, 5. Is this less than this?
Yeah.
Yes. Is this less than this? Yes. So we are now going to have 3, 4, 5. Is this less than this? Is this less than this? Is this less than this? You can see that if this list were really long, this would start to be a lot of questions as we get toward the end of the list and be yes, 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 yes. Whereas here, the very first question we asked, the question was no, and we could just stop. So that was the difference between the linear order of it being in order and the quadratic order of it being in reverse order. There are significantly more questions. We have to compare each element to every element that came before it, rather than just the first element. So best case performance is very different from its worst case performance. How about the average case? What can we expect on average?
Some could be sorted, some aren't sorted.
How many comparisons would you expect to make? So if we're at the position in the array that is something like, if we're at step somewhere in some arbitrarily long array, it just goes from somewhere. How many comparisons do you think you need to make if this is index 0 all the way over here and you're at step? Something like step over 2 on average, you'd expect it to be probably something like a uniform distribution between 0 and step, which the average would be about step over 2, so there'd be a large amount of variation. Sometimes you wouldn't have to do anything, sometimes you'd have to move it all the way back to the beginning, but on average, you move it about half the way. What order would that be in? One way to think of it is as step varies. The number of comparisons that we would need to make have this whole thing. So the number of comparisons we need to make here, we just start dividing these things by 2. If you divide each element of a sequence by 2, you can just sum the whole thing and divide that by 2. So this is going to turn this sum from n times n plus 1 over 2 to n times n plus 1 over 4, or 2 times 2, which is 4. Does this constant change the order? We're doing about half as much work. The answer is no, it does not change the order. This is still quadratic. So the average case of insertion sort is also quadratic. You would expect that on average, you do about half the work of the worst case. It turns out that this isn't horribly difficult, and many other algorithms' average case performance is significantly harder to figure out. And you can see that we had to do a little bit more work to figure out the average case performance than we did for the worst case or the best case performance, which is again why this question is a little bit more difficult to answer, and why frequently we just go with the worst case performance as a good approximation. But also, as I said before, usually this average case is closer to the worst case than to the best case. And in fact, here is an example of where we see the average case and worst case are the same order, and the average case and the best case are not the same order. All right, that is insertion sort. Does anyone have any last minute questions on insertion sort before we move on to our next basic sort? All right, we're going to talk about selection sort next. Just like before, let's start by taking a look at some pseudocode, which we've changed up the colors a little bit for this one. Take a while, stare at this, and see if you can understand it just from the pseudocode. Just from looking at the pseudocode, how do you feel about selection sort? Understand it perfectly? Yeah, I have no idea what this means. So when you read computer science textbooks a lot, the reason that I do this before we hop into anything else is that textbooks will just introduce an idea, give you the pseudocode, and then move on, which I don't think is the best way to learn something, but I want to give you some practice reading pseudocode and trying to understand the logic behind the pseudocode, because again, that's just how a lot of textbooks work, and you'll be able to glean a lot more from them if you have more practice with it. But let's actually go through an example of selection sort on the board so that we can make sure that this makes sense. Rather than having 10 elements, let's have a few. We don't have enough time for 10 elements. We're going to go through a 5-element array for the moment. Get out some numbers. 3.
94.
I like that. Next. 100. We almost did things in order, people. I'm going to make a couple of swaps here. Perfectly okay for things to be in order. I think it'll be a little bit more illustrative to have things a little bit out of order. All right, so we're going to go through this size minus 1 times. Size is 5. So we're going to keep a pointer to the current element. And actually, we should start the current element really. Yeah, we want it to be right here. We're going to have a piece of memory that we're going to call the smallest that we've seen so far. We're going to start that at 10 as the element that we are looking at, and we are going to just move through all aspects of the unsorted array, since we're starting at the very beginning, and we're gonna identify what is the smallest number in that. So we're gonna have an iteration that says, for each of the unsorted elements, all of these, if the element is less than the current minimum, set the element as the new minimum. So we set this to be 10, and then we ask ourselves, is 100 less than 10?
No.
Is 3 less than 10?
Yes.
Yes, we're gonna write 3 into minimum. You guys still want there to be a little thing, right? Is -4 less than 3? Yes, we're gonna override 3 with the -4. Is 7 less than -4?
No.
No. So now what we're gonna do is we're gonna swap, we also need to store the location of this -4. So we have the location of this 10, and we have the location of this -4. We're going to do a swap of these two elements. So we're going to say that this is now -4, and this is now 10. How much of this is now in order, is now sorted? The first element. So we're going to bump this up now to point it here. And starting here, we're gonna keep track of. So I guess I'm also going to include a piece of memory here that I'm gonna call something like min loc, which is the location in the array of where we found that minimum. So we're going to set this to be the first unsorted element of where we are right now. Is 3 less than 100? Yes, we're going to write 3 here and 2 here, saying this is the index of where we found that 3. Is 10 less than 3? Is 7 less than 3? So we're gonna swap the current location 1, the min location 2. So we're gonna take whatever is here and whatever is here and swap them. How much of the array is now sorted? The first 2 elements. So we're going to bump up our current location to point here. We are then going to set our minimum to that value. Erase this. I guess we can start it at 2. We need to make sure that we know in case that this does happen to be the minimum. Is 10 less than 100? Yes, so we're going to change this. Change this. Is 7 less than 10? Yes. So we're gonna set this to 7, this location to 4. So now we're gonna swap what's at the current position 2 with what's at the minimum position 4. And we still have to go through the verification process that 10 is less than 100, but we will see that it is. How intuitive is selection sort? Does this seem like this makes the process make sense? How do you think intuitively it compares to insertion sort? Do you think that insertion sort is more intuitive? Selection sort is more intuitive? Does anyone have an opinion on that? Selection is my personal most intuitive sort. Find the minimum, swap it in place. Find the next minimum, swap it in place. Find the next minimum, swap it in place. If you ever have to implement a sort, go with whatever is most intuitive. This is what is going to take the least time probably to implement. If man hours are what's important to you, then this will be probably what you can implement the fastest. How much time do we have? We're basically out of time. So between today and Monday, if you'd like something else to do, take a stab at implementing selection sort. And we will come implement it in person on Monday.